In modern precision manufacturing, a fraction of a millimeter is the difference between a functional component and a catastrophic failure. A machine like a CNC mill, where computer numerical control automates the cutting tools, operates at high speeds with immense physical stakes. Even in these highly controlled environments, friction, heat, and material wear introduce unavoidable natural variation into the parts being produced. The primary goal of process engineering is to reliably fit that natural variation inside strict predetermined specification limits. This graph illustrates the baseline visual grammar of statistical process control. The rigid boundaries imposed by the customer's design are plotted as the lower specification limit on the left and the upper specification limit on the right. The physical output of the machine forms a normal distribution, or bell curve, between them. There are two spatial relationships at play here. The static, allowable gap between the LSL and USL is the tolerance. The fluctuating width of the bell curve itself represents the actual variation of the physical process. To evaluate how well that variation fits inside that tolerance, engineers rely on two distinct mathematical metrics: CP, the process capability ratio, and CPK, the process capability index. CP evaluates the theoretical potential of a manufacturing system. CPK evaluates its actual performance by penalizing processes that fail to center their output on the exact target. Confusing these two numbers is the primary reason an engineering department will look at a spreadsheet and assume they are producing perfect quality, while the factory floor is simultaneously shipping boxes full of defective parts. Looking at this diagram, we start with the mathematical formula for the process capability ratio, or CP. It calculates the ratio of available space to actual variation. The numerator, upper specification limit minus lower specification limit, represents the rigid, unchanging goalposts set by the customer's requirements. The denominator is 6 sigma. Sigma is the mathematical symbol for standard deviation, measuring how spread out a set of data is. 6 standard deviations capture the total physical spread of the manufacturing process's natural variation. This animation shows the exact threshold of capability. If a process scores a CP of exactly 1.0, the 6 sigma variation perfectly matches the width of the allowable tolerance. The edges of the output touch the limits, leaving absolutely zero margin for error. Mathematically, the lever for improvement is reducing the variation in the denominator. Shrinking the physical spread drives the CP score higher, pulling the edges of the curve away from the danger zones and indicating greater theoretical potential. This section of the chart establishes the baseline for an ideal capability report. An ideal process has high potential because the variation is small enough to fit comfortably inside the limits with room to spare, unlike the large variation process below it. But a high CP only proves the machinery has the precision to fit the tolerance window. It guarantees nothing about where it's actually aiming. The critical flaw in the CP formula is what it leaves out. It completely ignores the process mean. It is entirely blind to centering. This visualization models a scenario where a manufacturing process has excellent theoretical potential, represented by a tightly grouped, highly precise variance. Now we introduce a mechanical drift. The process mean shifts significantly off-center toward the upper limit, but the machine maintains the exact same narrow variance. The area where the curve breaches the limit physically represents the creation of defective, unusable scrap parts. Despite producing a high volume of defective parts, the CPCO score remains completely unchanged. Because the width of the curve never altered, the ratio of tolerance to variation remains identical. The third row introduces the official terminology, an offset process. It has capable potential, but physically produces defects on one side. The bottom left graphic reinforces this metric's footprint. Under lateral movement, CP stays constant, relying strictly on a fixed shape and 6 sigma range. Relying on a space measuring metric alone is an engineering hazard. CP calculates a failing off-center system, completely misses the defects, and reports it as capable. This panel introduces the Process Capability Index, or CPK. This is the mathematical solution designed specifically to penalize off-center targeting and calculate actual performance. This model breaks the CPK formula down. Instead of looking at total space, the formula visually isolates into 2 separate evaluations happening simultaneously. The first half of the equation measures the exact distance from the actual process mean down to the lower specification limit. The second half measures the distance from that same process mean up to the upper specification limit. The critical mechanism here is the minimum function. It automatically discards the safer, longer distance and strictly selects the shorter of the two measurements. CPK measures your capability relative only to your nearest point of failure. It represents the actual worst-case performance risk of the system. By anchoring the mathematics to the mean rather than the total spread, CPK transforms a theoretical capability metric into a practical, real-world risk assessment. This graphic highlights the foundational law governing statistical process control metrics. CPK is always less than or equal to CP. Translating that formula into reality means a manufacturing process's actual performance can never, under any circumstances, exceed its theoretical potential. This animation demonstrates the single, specific condition where the two metrics perfectly align. When a process is flawlessly centered, the actual performance matches the maximum theoretical potential. But watch the immediate penalization effect. The moment the process drifts off-center, the performance score drops rapidly, while the potential score completely ignores the error. The numerical gap between these two figures is specific data. It represents the exact process capability you are sacrificing strictly due to bad aim. This inviolable inequality is an instant diagnostic tool. It tells an engineer immediately whether a defect on the floor is caused by the machine's inherent lack of precision or simply due to the operator's poor targeting. This benchmark dial shows the industry standard target. To certify a manufacturing line, engineers must achieve a CPK of 1.33 or higher. Achieving this requires a specific response matrix. The relationship between CP and CPK dictates your factory floor intervention. If your baseline CP is low, the machine lacks the raw precision required for the job. You cannot center your way out of the problem. You must re-engineer the system to reduce the physical variation. However, if the CP is high but the CPK is low, the machinery is fine. The fix is a mechanical adjustment to re-center the main. This leaves process engineers with one final operational mandate: never accept a capability report that only lists one metric. Isolation breeds blind spots. CP tells you what your equipment is theoretically